We gaze into the cosmos, into the vast inky blackness between the stars, and we call it nothing, a void, a silent, inert backdrop. But what if we've been catastrophically wrong? What if that nothing isn't empty at all but a force? A terrible, relentless engine pushing the very fabric of reality apart? For eons, we assumed gravity was the universe's ultimate architect, pulling everything together, eventually slowing the cosmic dance. Then we looked closer. We saw something that shattered every single assumption. The universe isn't just expanding, it's accelerating. Galaxies are fleeing each other at ever-increasing speeds, driven by an invisible hand. This isn't gravity. This is anti-gravity. And the most chilling suspect for this cosmic betrayal isn't some exotic particle or field. It's the terrifying seething energy of nothing itself. What if the most powerful force in existence is the very emptiness we thought was inert? For nearly a century, our cosmic narrative was beautifully, reassuringly simple. The Big Bang ignited the universe, blasting everything outward, and ever since, gravity, the universe's tireless sculptor, has been working to pull it all back. We imagine the cosmos as a colossal projectile launched into the void, its initial explosive velocity gradually, inevitably, being reined in. Like a stone thrown skyward, we expected its ascent to slow, its momentum to wane, perhaps even to eventually fall back on itself in a fiery, big crunch. This was the prevailing dogma, etched into every textbook, a fundamental truth of our existence. Gravity was the architect, the unyielding law, and the universe's expansion was destined to decelerate, its cosmic dance slowing to a crawl. But then the late 1990s arrived, and with them, two audacious teams of astronomers, each locked in a silent intellectual race against time and each other. They weren't trying to break our understanding. They were simply trying to measure it, to put a finer point on the universe's expected slowdown. Their method was brilliant, elegant. Use type Ia supernovae as cosmic mile markers. These aren't just any exploding stars. They're stellar events, so consistently brilliant, so uniformly luminous, that they serve as perfect standard candles. Find one in a distant galaxy, measure how bright it appears to be, and you can precisely calculate its distance. Measure enough of them across vast stretches of cosmic time, and you can trace the universe's expansion history, charting its deceleration curve. It was a painstaking, almost sacred quest, akin to a detective meticulously gathering the faintest, most crucial clues at a sprawling, ancient cosmic crime scene. The teams, one spearheaded by Saul Perlmutter's Supernova Cosmology Project, the other by the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, pointed their most colossal telescopes into the abyss. Sifting through billions of light years, they hunted for the faint, fleeting echoes of these stellar detonations, each one a flash of insight from the universe's ancient past. The data trickled in, then streamed, then surged. Hundreds of supernovae, each a beacon from a different epoch. They plotted their positions, their brightness, their redshifts, and as the graphs began to form, a chilling, impossible picture emerged. The distant supernovae, the ones from billions of years ago, were fainter than they had any right to be. Not subtly fainter, but dramatically, undeniably fainter. Fainter meant they were further away than our decelerating universe model predicted. Farther meant the light had taken longer to reach us, and longer meant the universe hadn't slowed down at all. It had sped up. This wasn't a minor discrepancy. This was a cosmic violation, a fundamental betrayal of everything we thought we knew. Imagine dropping a coin, expecting it to hit the ground, but instead, it shoots upwards, accelerating away from your hand with a sinister, unseen force. That was the scale of the shock. The universe wasn't braking. It was stomping on the accelerator, pushing against its own gravitational pull. An unseen, unheard force was not just counteracting gravity, but dominating it, actively pushing galaxies apart at an ever-increasing rate, stretching the very fabric of space until it groaned. It was an anti-gravity engine, vast and pervasive, revealing itself in the cold, hard light of distant explosions. This was the universe's most profound secret, unveiled, tearing apart our cosmic map. And it screamed one terrifying question: echoing through the void. What is doing this? The universe, it turned out, was not decelerating. It was accelerating. This wasn't a tweak to our models. It was a cosmic paradigm shift. The implications were staggering. For the first time, humanity was faced with undeniable evidence that something utterly unknown, something profoundly alien to our understanding of physics, was not just present in the cosmos, but was the dominant force shaping its destiny. We had a crime, but no suspect. An acceleration, but no engine. The scientific community, reeling from this revelation, scrambled to find an explanation, to give a name to the invisible hand pushing the cosmos apart. And so, dark energy was born. Not a definitive answer, mind you, but a placeholder, a cosmic wanted poster for the most powerful and elusive entity in the universe. It's a name that perfectly captures our profound ignorance. Dark, because we can't see it, can't touch it, can't directly detect it. Energy, because it's doing work, immense work, on the largest scales imaginable. But this isn't just any energy. This is energy with a chilling, paradoxical property: negative pressure. Imagine pressure as a force that pushes outward, like air in a balloon. Negative pressure, then, is a force that pulls inward like a vacuum cleaner, or so logic dictates. But in the bizarre realm of general relativity, Einstein's masterpiece, negative pressure, behaves like repulsive gravity. It doesn't attract, it repels. It doesn't pull, it pushes, hard, everywhere, all the time. This isn't a localized burst or a directional push. Dark energy is thought to be uniformly distributed throughout the entire cosmos, permeating every cubic centimeter of space, from the heart of a galaxy to the deepest, coldest void between them. It doesn't dilute as the universe expands. It maintains a constant energy density. As space stretches, more empty space is created, and with it, more dark energy springs into existence, feeding its own relentless expansion. Think of it like this: if you have a certain amount of water in a bucket and you double the size of the bucket, the water becomes less dense. But if dark energy were water, doubling the bucket would create more water to fill the new volume, keeping its density exactly the same. This means its repulsive force never weakens, never gives up. It's an indefatigable, invisible tyrant, constantly adding more fuel to the cosmic fire. This is why it's so terrifyingly effective at tearing the universe apart. Gravity, while powerful, weakens with distance. The pull between two galaxies diminishes rapidly as they drift further apart, but dark energy's push, stemming from the very fabric of space itself, remains constant. At astronomical scales, beyond the gravitational grip of galaxy clusters, dark energy wins, always. It's like a colossal, invisible hand, pressing down on the accelerator of expansion, pushing the cosmic speed limit further and further into the impossible. The leading theory posits that dark energy accounts for roughly 68% of the total energy density of the universe. Yes, you heard that right. Over 2/3 of everything that makes up reality is this mysterious repulsive force, this cosmic ghost, this engine of expansion that defies our intuition. Normal matter, everything we can see, touch, and measure from the smallest atom to the largest galaxy, makes up a paltry 5%. Dark matter, another enigmatic entity that exerts gravitational pull but doesn't interact with light, accounts for about 27%. But the true king of the cosmos, the silent, dominant force, is dark energy. It's the ultimate cosmic paradox. The universe is mostly made of something we don't understand, something that actively pushes it apart. We are living in a universe dominated by an unknown force, an entity that is not just pulling us, but pushing us towards an uncertain, perhaps desolate future. This isn't just a scientific puzzle, it's an existential one. It forces us to confront the profound limits of our knowledge, to truly grasp how little we understand about the reality we inhabit. If you're captivated by these cosmic mysteries, if you want to keep exploring the darkest corners of existence with me, then hit that like button and subscribe. Join the expedition as we probe the universe's most profound secrets. So, we have dark energy, the invisible suspect, the force with negative pressure, the cosmic accelerator. But what is it? Where does it come from? This is where the story gets truly unsettling, because the most compelling, yet deeply problematic candidate for dark energy isn't some exotic new field or a hidden dimension. It's the very nothing we thought was just, well, nothing. It's the intrinsic energy of the vacuum itself. This idea, seemingly simple, plunges us into the mind-bending world of quantum mechanics. In our everyday experience, a vacuum is empty, a perfect void. But at the quantum level, empty space is anything but. It's a seething, roiling foam of activity. Particles and antiparticles constantly pop into existence, briefly borrow energy from the vacuum, and then annihilate each other, vanishing back into the quantum ether. These are virtual particles, fleeting ghosts that defy our classical understanding, yet their existence is predicted by our most successful theories and confirmed by subtle measurable effects like the Casimir effect, where two uncharged metal plates placed incredibly close together actually push each other, forced by the quantum fluctuations of the vacuum between them. It's as if the nothing inside the plates has less energy than the nothing outside, creating a tiny persistent push. If empty space is truly a quantum maelstrom, a churning ocean of virtual particles, then this vacuum energy should have measurable consequences. Specifically, it should exert a repulsive force, acting exactly like dark energy. The idea is elegant, beautiful even. The very fabric of space-time, infused with this inherent quantum energy, is the engine of cosmic expansion. The nothing isn't inert, it's alive, buzzing with latent power, and it's pushing everything apart. This theory offers a tantalizing explanation, connecting the largest scales of the universe to the smallest quantum fluctuations. It suggests that the same laws that govern the subatomic world also dictate the fate of galaxies. The universe isn't expanding because of some external push. It's expanding because of its own inherent quantum nature, because nothing is fundamentally something. But here's where the elegant theory crashes headlong into the most colossal, embarrassing, and baffling discrepancy in all of physics. If we calculate the amount of energy that should be present in the vacuum based on our quantum theories, the energy of all those virtual particles popping in and out of existence, the number we get is astronomical, truly astronomical. It's a number so gargantuan, so mind-bogglingly immense, that it defies comprehension. We're talking about a vacuum energy density so high, it would cause the universe to expand so violently that it would tear itself apart almost instantly. Before a single star could form, before atoms could even coalesce, the universe would have ripped itself into subatomic shreds. Our calculations predict a vacuum energy that is something like 10 or 120 times larger than the observed value of dark energy. That's a 1 with 120 zeros after it. It's a discrepancy of 120 orders of magnitude. This is not a small error. This is not a rounding mistake. This is like calculating the weight of a grain of sand and getting the mass of the entire observable universe. It's the largest mismatch between theory and observation in the history of science. It's been called the worst theoretical prediction in the history of physics. So we have a profound paradox. The vacuum energy hypothesis provides a perfect candidate for dark energy, something that is everywhere, has negative pressure, and doesn't dilute. But the amount of vacuum energy predicted by our most successful theories is so absurdly, catastrophically large that if it were true, we wouldn't be here. The universe wouldn't exist as we know it. This means one of two things. Either our understanding of quantum mechanics is fundamentally incomplete when applied to gravity and cosmology, or there's some unknown mechanism, some cosmic eraser, that is canceling out almost all of this vacuum energy, leaving behind only the tiny residual amount we observe as dark energy. We are missing 119.99999 orders of magnitude of energy. It's as if the universe is performing an exquisite, impossible balancing act, canceling out quadrillions upon quadrillions of joules of vacuum energy, leaving just enough to accelerate expansion, but not so much that it rips reality apart. The nothing is indeed something, but why is it so precisely, so ridiculously small compared to what it should be? The most powerful force in the universe is a phantom, a whisper of what our theories predict, an almost perfectly canceled cosmic debt. What kind of cosmic ledger keeps such a meticulous, precise balance? It's the ultimate cosmic riddle, etched into the very fabric of the void. If dark energy, this intrinsic energy of nothing, is indeed the dominant force in the cosmos, then its implications for the universe's ultimate fate are chillingly profound. For billions of years, the universe has been playing a cosmic tug-of-war. For the first few billion years after the Big Bang, matter and its gravitational pull were the undisputed champions, slowing the initial expansion. Galaxies formed, clustered together, and the universe began to build its grand structures. But then, about 5 to 6 billion years ago, dark energy, the silent usurper, began to assert its dominance. Its constant, unyielding push, unlike gravity's diminishing returns, slowly but surely began to win, and it will continue to win relentlessly until the very end. Imagine a colossal cosmic balloon. As it inflates, the galaxies painted on its surface drift further apart. For a long time, the balloon's expansion was slowing, but now it's not just inflating, it's accelerating, inflating faster and faster. And because dark energy doesn't dilute, because more of it appears as space expands, this acceleration is not just a temporary phase, it's the new, terrifying normal. What does this mean for the future? It means a universe destined for an unimaginable, desolate end. We're not talking about a big crunch, where everything collapses back into a singularity, nor are we heading for a gentle big freeze, where the universe simply cools down and fades into eternal darkness. Instead, the triumph of nothing will lead to a scenario far more extreme. The Big Rip. As dark energy continues to dominate, its repulsive force will grow stronger relatively to gravity. First, galaxy clusters like our own local group will become gravitationally unbound from each other. Andromeda is currently hurtling towards the Milky Way, destined for a magnificent collision. But in the far, far future, other clusters will be pushed away from us so violently that their light will eventually redshift beyond detection, fading into an infinite, unreachable distance. Our observable universe, once teeming with billions of galaxies, will shrink to just our local group, a solitary island of stars in an ever-expanding, increasingly empty void. The cosmic neighborhood will become an infinite, desolate wasteland. But the Big Rip doesn't stop there. The relentless push of dark energy won't just separate galaxies. It will begin to tear apart the very structures within galaxies. Eventually, the immense gravitational pull that holds galaxies together, that sculpts spiral arms and binds stars into magnificent systems, will be overwhelmed. Stars will be ripped from their galactic moorings, flung out into the desolate intergalactic space. Our own Milky Way, once a vibrant cosmic city, will dissolve, its stars scattering into the expanding darkness like dust motes. And it won't end there. The scale of destruction will continue to shrink. Gravitationally bound systems like our solar system, where the sun holds its planets in a delicate dance, will eventually succumb. Planets will break free from their stars, becoming rogue worlds, forever drifting in the cold, dark, rapidly expanding emptiness. Even the stars themselves, with their immense internal gravity, will eventually be ripped apart, their nuclear furnaces extinguished, their very atoms pulled asunder. The Big Rip predicts that the repulsive force of dark energy will ultimately become so immense, so overwhelming, that it will overcome the fundamental forces that bind matter together. Molecules will be torn apart, atoms will be ripped into their constituent electrons and nuclei, and finally, even the nuclei themselves, and then the quarks within them, will be disintegrated. The universe will dissolve into an infinitely dilute, cold, and utterly empty soup of fundamental particles, scattered beyond all recognition, beyond all interaction. Nothing will have truly won, reducing everything that ever was, every star, every galaxy, every particle, into an uncommunicable, disconnected oblivion. This is the chilling legacy of nothing, the vacuum, the void, the very emptiness of space. It's not just a passive absence, it's an active, destructive force, silently, relentlessly, pushing the cosmos towards its most desolate possible end. The universe isn't just expanding, it's being devoured by its own emptiness, pulled apart from the inside out by the very fabric of reality itself. It's a cosmic horror story, written in the language of physics, where the most powerful force in existence is the one we once dismissed as inert. The universe, then, is not what we thought. It's not a grand, self-contained system slowly winding down. It's a vast, accelerating expanse, driven by a force so profound, so counterintuitive, that its very existence challenges our deepest assumptions about reality. The greatest mystery isn't what exists, but what nothing is. It is the pervasive, relentless engine of expansion, the cosmic anti-gravity, the silent, invisible architect of our ultimate fate. We live in a cosmos where emptiness isn't void, but power, where the silence between the stars isn't a lack of something, but the presence of an overwhelming force that will eventually tear everything apart. It's a universe dominated by a vacuum that isn't empty, but seething with an energy we can barely comprehend, an energy that should be astronomically larger than it is, yet somehow, miraculously, is just small enough to allow stars and galaxies and life to exist for now. This paradox, this cosmic tightrope walk between existence and instantaneous dissolution, is perhaps the most profound revelation of our age. It means our very presence is an improbable miracle, a brief flicker of complexity in a cosmos destined for infinite dilution. Tell me what you liked or disliked about this video. What do you think could be changed to make it better? I read every comment and will respond to every suggestion.